Okay, hi everybody. Thank you so much for having me here. Even though it's remote, I know that it can be a little bit challenging to stay engaged through a remote talk, so I'll try to make this as entertaining as possible as we go.
Wow.
How's my sound? Good.
We,
Okay.
we're we're working on getting you a little bit louder
Okay.
now.
I'll keep talking as you do that.
Yes.
Okay. So I'm an associate professor at UC Santa Cruz. I have very fond memories of attending the Sagan Summer School as a graduate student, and so I hope you're all getting a lot out of this week there at Caltech. Okay, so I'm going to go ahead and get started. If someone comes up to the podium and gives a thumbs up or thumbs down, I'll try to respond to that. But I'll just
I
get
think
going.
you're good to go. I think you're good to go now.
Okay, wonderful. Okay, so this talk is about wavefront sensing and control. So first, I just wanted to make sure that we're all on the same page about what a wavefront is. So if we think of light's electromagnetic field, and we consider a star who's emitting light uniformly in all directions, then the surfaces of constant phase in the starlight's electric field are what we refer to as a wavefront. So a good analogy to consider is if you dropped a pebble into a pond, as you see in this figure, and you see the waves rippling outward, you could draw circles along, for example, the crests of those waves. Those would be the surfaces of constant phase. Those would be your wavefronts. Okay, so now if we're imagining a star that has these circular, or if we were in 3 dimensions, spherical wavefronts that it's emitting uniformly in all directions, then by the time that starlight reaches us on the Earth, those spherical or circular wavefronts are so stretched out that we can pretty much think of those as being plane waves, as being flat. So those starlights wavefronts are traveling to our telescope. If we had an idealized space telescope, then we would bring that light to a focus and we would have our idealized airy disk. And in some of the optics lectures that you had yesterday, you were probably acquainted with the point spread function, the classic airy disk whose full width half maximum is approximately lambda over d. So with no turbulence or no other optical aberrations, that is the characteristic size of your point spread function. With atmospheric turbulence, that image size is going to be much larger, typically on the order of something like half an arc second to even 2 or several arc seconds in very poor seeing. Even space telescopes have to contend with the effects of optical aberrations. So the Hubble Space Telescope famously was accidentally launched with the wrong prescription, and that led to poor image quality until that was corrected with upgrades later. Telescopes that are segmented, like the James Webb Space Telescope and like the future plans for the Habitable Worlds Observatory, are going to have segmented primary mirrors. And those primary segments need to be very precisely co-phased. So the positions or the pistons of those segments have to be aligned. The tip and tilt of each of those segments also has to be just right. And if they're not just right, that also leads to optical aberrations. Similarly, as the starlight passes through the optics in a space telescope, it's going to encounter different imperfections in those optics that are going to lead to aberrations. The light's path through those optics is not going to be exactly uniform over time. For example, due to pointing jitter, due to thermal variations in that observatory. So some way of dynamically correcting for optical aberrations is very much needed in space-based telescopes, especially in a high contrast imaging context, as well as ground-based telescopes. Okay, but of course, ground-based telescopes have very particular challenges. So as the starlights or astrophysical objects wavefronts propagate through the atmosphere, it encounters different pockets of air, and those pockets of air are going to have some slight temperature variations between them. And those temperature variations give rise to index of refraction fluctuations. And so some parts of the wavefront are going to be delayed relative to other parts of the wavefront. So this is how the atmosphere gives rise to wavefront aberrations. So instead of that perfect airy disk, what we might see on the ground if we were taking millisecond exposures might look something like this animation. So what we're seeing with our telescope are images that are representative of a combination of many airy disks at different locations. And these are called speckles. So each of these area disks is still defined by the diffraction limit of the telescope, but now you have many realizations. And of course, the centroid of this entire PSF is moving around. So that's where we get image motion, as well as the image blur. So this is what we have to deal with in a ground-based telescope. Now, where does turbulence arise? So turbulence can arise in a large variety of locations. So starting with inside the dome of your observatory, it may be that the telescope's mirror is hotter and takes longer to cool down than the air in the dome surrounding the mirror as the night goes on. And so the mirror is giving off heat, and that can lead to turbulence just next to the surface of the mirror. Similarly, you can have what's known as dome seeing. As air is blowing through the dome, you can set up turbulence even inside the dome. That's why you'll see observatories are designed with specialized openings and lues to try to influence how the wind flows through the telescope to minimize this kind of dome seeing and the wake behind the observatory. We also have turbulence at what we call the boundary layer. The boundary layer is the lowest part of the troposphere, the part of the atmosphere that we live in, that's directly influenced by the Earth's surface. So it's responding to forcing from surface on, say, hour-long timescales. Now, above the boundary layer, so above a kilometer or so, we have what's known as the free atmosphere, where you might have turbulent wind layers with some fairly constant velocity. And then as we continue upward through the atmosphere at about 10 kilometers, we have the tropopause. This is the transition between the troposphere and the stratosphere. And so oftentimes we'll see turbulence peaking near the tropopause due to a strong wind shear. So wind of different velocities that's kind of colliding at the tropopause. Okay, so an adaptive optics system or any kind of wavefront sensing and control system is designed to correct for optical aberrations in real time. So if we imagine our aberrated starlight here at the top that's been collected by our telescope and directed to our adaptive optics instrument coming in on the upper left-hand side, the first thing it typically encounters in your AO system is going to be the deformable mirror. Okay, so a deformable mirror in an idealized scenario works something like this. So on the left-hand side, you see an incoming wave with some kind of step function wavefront aberration you see there. So some part of the wavefront here is sort of ahead of the rest of the wavefront. Now, that wave is going to encounter the deformable mirror. And the deformable mirror has a shape that's designed for the part of the wavefront that's ahead of the rest to now be appropriately behind the rest of that wavefront. So that after the light has bounced off of the DM, that wavefront has become flat again. Now, there are different designs of deformable mirrors. There are what's known as continuous phase sheets. So you can have one single mirror surface, and then behind that mirror, you might have some kind of actuator that's pushing and pulling that continuous mirror surface. We also have segmented deformable mirrors. So you might have, say, hexagonal segments, kind of like a miniature version of a segmented space telescope mirror. And those might be pistoned and tipped and tilted. But all of these in an adaptive optics context are designed to do the same thing, which is correcting for the wavefront aberrations. So I'd like to talk a little bit more about the key requirements for a deformable mirror. Okay, so one of the most important requirements has to do with the number of deforming elements or the number of degrees of freedom that you have on your DM. So a good way to think about this has to do with the spatial scale of atmospheric turbulence. So the spatial scale of turbulence is described by what's known as the Freed parameter, or R naught. Some of you may have yourself or have seen, we have these mugs from SPIE a couple of years ago that says we are not seeing limited. So that was in honor of the late Freed, who passed away a couple of years ago. So we could spend an hour, 2 hours deriving the Freed parameter, R naught. But instead of doing that today, I'm just going to quote the definition of R naught to you now. So R naught has to do with the wave number K, the zenith angle Z, and then the integral of what's called the CN squared profile, which is really just a measure of the strength of the turbulence at different heights in the atmosphere. And then this definition of the free parameter is based on Kolmogorov statistics, and that's where the minus 3/5 power law comes from. So if we imagine, as in this figure, that we have our primary mirror, we have the wavefront that's been affected by atmospheric turbulence arriving at our primary mirror, we can think of the characteristic length of these wavefront variations due to turbulence as being about R naught. So we need to have about R naught degrees of freedom on our deformable mirror across the DM. So in other words, the total number of subapertures on the DM should be about D over R naught squared. And R naught is, of course, a wavelength sensitive quantity, so you'd want to make sure to evaluate that at the wavelength that you plan to do your observing. So that tells you something about how many degrees of freedom that you're going to need on your deformable mirror. Another key requirement has to do with the dynamic range. So how much do you have to be able to deform the DM? So again, from turbulence theory, we can derive that the variance across the wavefront scales as the diameter of your telescope divided by that all-important R naught parameter to the 5/3 power. So for Keck, this is going to be something like a few microns, but for ELTs, it's going to be tens of microns because it depends on the diameter of your telescope as well as R naught. So this is partly why designing DMs for next generation large telescopes can be a technical challenge. This is also the reason why systems such as the Gemini Planet Imager will use two different deformable mirrors to do their correction. They act like a woofer-tweeter speaker system where one has a larger number of actuators, but with a smaller amount of stroke or smaller amount of change that they can create. And then they will also have a low-order deformable mirror that will have fewer actuators, but which have a larger dynamic range or larger stroke. Now, the second one I wanted to highlight is the temporal response of the DM. So the DM should be able to respond much faster than the characteristic timescale of atmospheric turbulence. Now, the characteristic timescale or coherence length of atmospheric turbulence is given by that Freed parameter divided by the wind velocity, where we can weight the velocity based on the CN squared profile that tells you about the strength of turbulence as a function of height in the atmosphere. So a good rule of thumb is that the DM should be able to respond, at about the 0.01 times the coherence length time scale, which is, maybe a millisecond or so in the near IR. And then finally, the influence functions on a DM need to be a good match between how thick the deforming surface is and how widely spaced your actuators are. So for example, if your mirror is too thin, then when you poke one actuator, you might get an overly isolated bump. However, if it's too thick, then you might have some large section of the mirror that's displaced when you poke only one actuator. And then finally, there are other considerations such as the surface quality. You don't want it to be too rough because you're not going to be able to correct that given that this is the optical element that you're using to do the correction. Hysteresis and power dissipation, etc. So here are a few images of different DMs. You have continuous phase sheets. You have MEMS devices that are more on the scale of a centimeter. These Zionetics ones that I showed are on the scale of tens of centimeters. And then you also have adaptive secondary mirrors where the secondary mirror of your observatory becomes the DM, and those can be on meter scales. There's a lot of interesting technology development going on in the field of adaptive secondary mirrors right now. So far, most deformable secondaries have been based on voice coil actuators. And it's pretty amazing because the mirror itself is actually being magnetically levitated off the rest of the structure. And there's recently been a lot of work led by my colleague Phil Hinz here at UC Santa Cruz and working with a company in the Netherlands called TNO on an alternative technology for adaptive secondary mirrors where you don't have that air gap and where you might have some different opportunities for power dissipation and other things. So DMs are still very much an active area of development. Okay, so the next thing that we want to go to in our diagram of the AO system after the light has bounced off of the deformable mirror is the wavefront sensor. So oftentimes you'll split the light by wavelength. For example, you might send the red light to your science instrument and the bluer light to your wavefront sensor. Okay, so a wavefront sensor is just an optical device that's designed to transform the phase or the wavefront variations into some intensity that's easy for us to measure. So some of the requirements on a wavefront sensor is the spatial resolution. So you need to be able to reconstruct the wavefront at about the same or better spatial resolution as the DM can correct it. It also has to have the right balance of dynamic range and sensitivity for your application. Usually these two things need to be traded against one another. So for dynamic range, you need to be able to measure the scale of the aberrations that the atmosphere is giving you, for example. And then for sensitivity, you also need to be able to measure sufficiently small amplitude aberrations to meet your final wavefront sensing requirements. Like the DMs, it has to be able to run fast enough to keep up with atmospheric turbulence. And another point that we'll go into more later is we have to have some understanding of the linear range. So the range over which you have a linear relationship between the input phase variation and then the output intensity variation that you can measure. We also want an efficient use of photons. And then for more generalized astrophysics purposes, it's convenient if your wavefront sensor can work for extended sources as well as point sources and work over a large range of wavelengths. Okay, there are many ways that you can classify wavefront sensors, but one convenient way to put them into two categories are to think of them in terms of pupil plane and focal plane wavefront sensors. So in a pupil plane wavefront sensor, you're measuring the shape of the wavefront by looking at the light in the pupil plane and maybe splitting it up into different subapertures and measuring the intensity in each one. So I'll talk about the Shack-Hartmann and the pyramid wavefront sensor, which are two examples of pupil plane wavefront sensors. Now, we also have focal plane wavefront sensors that are measuring the shape of the wavefront from the focal plane. And we'll talk a little bit more about those as well. So one of the most commonly used wavefront sensors on sky is the Shack-Hartmann wavefront sensor. So the Hartmann part of the Shack-Hartmann wavefront sensor was originally a test for measuring the quality of an optic by putting a grid of holes in front of that optic and then observing the effect in the far field. This was modified by Roland Shack in the 1970s, where instead of having that sort of screen with holes, now we have an array of lenslets. And this is a lot better when it comes to light efficiency. So the way to think about a Shack-Hartmann wavefront sensor is you have your light coming in collimated space. It encounters this array of lenses, and then you have a detector one focal length behind the lenses. So if you had no wavefront aberrations, you would just see a grid of equally spaced spots behind that grid of lenslets. But if you have some wavefront aberrations, each one of those lenslets is going to see a slightly tilted wavefront. And so that means that the spot associated with that lenslet will be correspondingly offset. And we can use the offset of that spot to reconstruct the local slope of the wavefront at that lenslet. So here is an example of how real-time Shack-Hartmann wavefront sensor data would look. So you see all of these different spots whose centroids are varying over time with atmospheric turbulence. So let's talk in a little bit more detail about how we would actually reconstruct the shape of the wavefront using a Shack-Hartmann wavefront sensor. So in this figure, you see the primary mirror. The light is collimated. And then we image the pupil on the lenslet array. And then we have our camera one focal length behind that lenslet array. So we can calculate our demagnification here just with the ratio of the telescope's focal length to the collimating lens focal length. And then the relationship between the displacement of the spot, that's delta x here, and the slope of the wavefront, that's phi here, is just based on the wave number k that magnification that we just discussed, the focal length of the lenslets, and that's really it. That's how you can translate one from the other. So let's look at a specific example here. So now what we're looking at is just one spot, so behind one of the lenslets of a Shack-Hartmann wavefront sensor. Let's imagine that we're sampling that spot with 4 pixels, so this is called a quad cell. So here's the spot, it has some diameter b. We can now use a pretty standard sort of center of mass equation to say, okay, how are we going to calculate the displacement in terms of x on this diagram and then y on this diagram. And we can then say, okay, our signal in x is just going to be this weighted intensity difference here. And if we call that value our signal, we can then plot that signal versus the spot displacement in the x or in the horizontal direction here. And that's what we're seeing in this figure. We would see that our signal has some slope here, given by 2 over b, the size of the spot. Okay, now you could think to yourself for a moment, what would happen if the displacement of the spot is greater than the radius of the spot? Let's give you a second to think about that for just one moment. So one way to think about that is what would happen if this spot moved in x so that the spot was entirely on I2 and I1 and none of the light was on I3 and I4. So this is a case where you have what we can think of as a rollover in the signal. So if the spot was entirely on just 2 out of the 4 pixels, then you would no longer be reconstructing the correct slope of the wavefront. So this is something we refer to as saturation in our reconstructed wavefront signal. So this is one example of an error in your wavefront reconstruction. We can talk about several different kinds of errors and how we can address them for the Shack-Hartmann. So for one, if you're designing a new Shack-Hartmann wavefront sensor, you can decide how many lenslets you want to have. So in the previous example that I gave, you might say, okay, well, if my wavefront is going to be saturated, maybe what I can do is just increase the number of lenslets. I can have more and smaller lenslets. So if you increase the number of lenslets, you are in fact increasing the sampling of the wavefront slopes, which increases the spatial resolution of your wavefront sensor. But you're still dealing with the same number of photons as you were before. And so that decreases the signal to noise on the wavefront reconstruction, and it therefore decreases your sensitivity. Okay, now we could also think, well, I could have dealt with that saturation by defocusing these spots, so just make the spots bigger. So if you increase the spot size, then sure enough, you are increasing the dynamic range of this wavefront sensor, but your computation of the centroid is going to be less accurate. And so that leads to a decrease in the sensitivity of your wavefront sensor. So this is highlighting over and over again the fundamental trade-off in wavefront sensing between dynamic range and sensitivity. Okay, now we can also consider the effect of the number of pixels. I could say, okay, instead of having 4 pixels per wavefront sensor spot, now I'm going to have a 4 by 4 pixel grid. So if I increase my number of pixels, then I also increase the centroiding accuracy. But again, my photons are more spread out, and so that's going to hurt my signal to noise. Okay, so next I want to talk about a class of wavefront sensors called Fourier filtering. This is when you place some kind of amplitude or phase mask at the focal plane and you see what happens in the pupil plane. So the most famous example of a Fourier filtering wavefront sensor right now is called the pyramid wavefront sensor, which those of you who are involved in adaptive optics might have heard about. So the way a pyramid wavefront sensor works is you put a pyramid-shaped piece of glass, or it may not literally be a pyramid-shaped piece of glass. It could be something that produces the equivalent effect. But you put that right at your focal plane. So you're focusing the light right onto the tip of that pyramid. So then your PSF gets divided into 4 quadrants based on which face of that pyramid it's falling onto. Okay, so now we have some intermediate optics to form an image of the pupil. And so now we have these 4 images of the pupil that were affected by these 4 quadrants of the mask. So a good way to think about how to reconstruct the wavefront using a pyramid wavefront sensor is to draw an analogy to the Shack-Hartmann. So in the Shack-Hartmann, we had these 4 pixels to sample each spot. Now we can imagine that we're using the pyramid wavefront sensor to say, well, now I have 4 images. So I'm going to translate those 4 pixels into the 4 equivalent locations on each of these images. And then we could reconstruct the wavefront accordingly. Okay, so in the interest of time, I'm going to then go to the Zernike wavefront sensor. This is another wavefront sensor that involves putting some kind of mask at the focal plane and looking at the effect in the pupil plane. So here, this was originally developed actually for microscopy. So it's a very old technique, but that has only recently been adopted more and more by astronomers. So the way that this works is you put a mask at the focal plane that has some little dimple in it. We call this the phase dimple. So the PSF of the star is sort of centered on this dimple. So now you're creating interference between the light that was delayed by the dimple and the light that was not delayed by that dimple. And then you're observing the effects at the pupil plane. The advantage of the Zernike, one of the advantages, is that it's very sensitive, but as before, it has a very small dynamic range. Now, one of the useful things about the Zernike wavefront sensor is that it is very effective at measuring these segmented mirror pistons. So this is something that taking advantage of the Zernike phase mask inside the CAPIC instrument that's led out of Caltech that my group got to do. So we were able to push 3 different segments on Keck's primary mirror. And then this is the resulting image, slightly reduced from our Zernike wavefront sensor, where we could see those effects. And then just recently, my postdoc, Maisa Salama, showed that by closing the loop on the primary mirror using that Zernike wavefront sensor inside the CAPIC instrument, that she was able to improve the image quality consistently by doing so. So each vertical pair of images here is before and after closing the loop on the primary mirror. Okay, so then lastly, I'm going to touch only very briefly on focal plane wavefront sensing. This is a huge topic that's extremely relevant to exoplanet imaging because we're often in a regime where non-common path aberrations or aberrations that arise after the main AO system's wavefront sensor start to play an increasing role in our sensitivity. And Nem Jovanovic, who hopefully some of you have a chance to meet while you're visiting Caltech, has a really nice overview of focal plane wavefront sensing techniques in his 2018 paper. But what I'll just emphasize right now is that if you recall that the focal plane intensity is related to the electric field times its complex conjugate, that's a reason why you're losing the sign information of the phase. So another way of saying the same thing is that if I am observing my PSF in the focal plane and I see that it's out of focus, I don't know whether it's inside of the correct focus position or outside of the correct focus position. I have no way of knowing that sign information. So that's why if you're trying to do focal plane based wavefront sensing, you need to introduce or otherwise find some kind of naturally occurring variation or diversity to help you break that sign degeneracy. So some of the pros of focal plane wavefront sensing are that if you're using your science detector itself as a focal plane wavefront sensor, you can measure those non-common path aberrations and then go on to detect them with your DM. You also have minimal aliasing if you're doing your wavefront sensing at the focal plane. And you also can make very efficient use of your photons. Some of the cons are that most focal plane wavefront sensors, in fact, all that I know of, don't have sufficient dynamic range to contend with atmospheric turbulence. So oftentimes these have to work as a second stage wavefront sensor after you've already cleaned up the wavefront with some first stage AO system. Also, they tend to be inherently chromatic because the focal plane image is going to be magnified or demagnified based on the wavelength. One famous example of focal plane wavefront sensing is a technique called Speckle nulling. So I'm giving an example here from Mike Bottom's 2019 paper. And here, what he did is he looked at a specific region around the PSF. And he computed, okay, based on the location of this speckle and how bright that speckle was, can I put a corresponding sinusoid on my DM to cancel out or null out that speckle? And so that's one way that you can do focal plane wavefront sensing. Now, just by measuring the location and the amplitude of that speckle, you don't have sufficient information to know sort of the directionality of that sinusoid that needs to be on or the sign of that sinusoid that needs to be on your DM. So you have to use your deformable mirror to probe, to sort of introduce diversity with the DM itself in order to do that speckle nulling. Now, this is just one out of a huge range of techniques for speckle nulling, so I encourage you to explore this topic further if this interests you. Okay. Now, one more topic that I wanted to touch on is laser guide star AO. So this is a great video showing, I think there are actually 4 total lasers, but here there are 3 lasers being used on Mauna Kea at the Subaru telescope and then the 2 Keck telescopes over the course of the night. So we use a laser guide star if there's no sufficiently bright natural guide star for us to use. So an example of, in an exoplanet science context, of when you might want to use a laser guide star is, for example, if you want to try to do exoplanet imaging in a very obscured region, or otherwise if you wanted to look for companions around stars that are so dim that you don't have enough photons to do your wavefront sensing with them. So that's a situation in our field where you might want to use laser guide star AO to extend the sort of range of stellar brightnesses that you could use in your search for companions. There are 2 types of laser guide stars that are currently in use. They're Rayleigh and sodium. So the sodium guide stars, all 3 of the ones that I just showed in the previous video are examples of sodium guide stars. These work by exciting atoms in a thin layer of sodium that exists at 95 kilometers in our atmosphere. It's mostly deposited there by meteorites. So by exciting these atoms, they will then fall back down to their ground state, emitting light at the same wavelength. And it's that light that you use on your wavefront sensor as artificial starlight. Rayleigh guide stars, instead of exciting atoms, they scatter off of air molecules, typically at around 10 kilometers. So the higher altitude of the sodium layer means that you'll get a better correction using a sodium guide star because the light traveling back to your wavefront sensor has experienced more turbulence corresponding to a greater amount of the heights through the atmosphere, whereas the Rayleigh guide stars have only experienced the turbulence up to 10 kilometers. The Rayleigh guide stars, however, they tend to be lower cost, and they also tend to be closer to eye safe, so they don't require as much coordination with, for example, the FAA to use. Okay, excuse me. So I'll just end by giving a quick summary here. So we need wavefront sensing control both for ground and for space-based telescopes, although the challenges of these 2 regimes are very different. And a wavefront sensor is a very broad term that just refers to any optical device that you can use to transform phase into intensity. And there are a lot of different ways that we can classify wavefront sensors. I introduced you to a few. All of the ones that I mentioned are examples of using classical optics. What I haven't mentioned so far are wavefront sensors based on photonic devices. So some of you might have heard the term, for example, photonic lantern. This is a fiber-based focal plane wavefront sensor that has been starting to be used more and more over the last couple of years. So I'm happy to take questions about that. Another thought that I wanted to leave you with is that we can really think of wavefront sensors and coronagraphs as 2 sides of the same coin. Both wavefront sensors and coronagraphs involve placing mass at focal planes and pupil planes designed to affect the amplitude and the phase of the starlight. And I think as time goes on in our field, we're going to start to merge those 2 devices more and more. If these topics pique your interest, I hope you'll consider joining us for the AO Summer School, which we hold each August at UC Santa Cruz. And I want to invite all of you to register at the URL that I've given here. So with that, I'm happy to take any questions.
Awesome. We have a good amount of time for questions. Actually, how about people actually come physically down here if you want to ask questions so we can actually, so Becky can possibly see you. So if you would like to ask a question, come to the microphones. And we'll. Right.
Where would you like me to be?
If you're at the podium, I'll be able to see
Okay.
you.
Hi, Becky. It's Eva Paris Observatory. I actually wanted to ask a question because you put one specific point on your summary slide, which is the wavefront sensors and the chronographs being two sides of the same coin. Incidentally, both you and David Duhlmann, who talked about chronography yesterday, showed one particular concept, which is about making a focal plane optic that acts on the phase in your focal plane, except you showed the Zernike wavefront sensor and David Duhlmann showed the Rodier and Rodier chronograph. And I wanted to ask you, are those literally the same implementation of the same thing? Is this, we know that the Rodier and Rodier chronograph has some limitations in terms of its chronographic performance, but how do those two concepts go together, considering that physically they're doing the same thing with the electric field, except that the chronograph reimages the pupil in which we have the phase information as intensity?
Yeah, so really, here, I'll go back to the Zernike slide here. So the Rodier chronograph and the Zernike phase mask are just two ways of creating interference of the starlight with itself. If you want to make a chronograph, then you want to have the phase offset be such that that starlight is nulled. And if you want to make a wavefront sensor, then you don't want it to be nulled. And it's really just what kind of phase offset are you introducing into the starlight? I think that's really the only key difference here. And so I think a question for us as a field going forward is how can we merge these two things?
Thanks a lot.
Great. If you can just go over.
Yeah. Hi, I'm Elle. It's so much scarier to ask a question from the front of the room. But I was wondering, since presumably you have to run the AO system at the same time as you're doing your observing in order to keep up with everything, how much flux do you have to redirect, and how does that affect your the sensitivity of your actual science observations?
Yeah, so that's a good question. So typically, ground-based AO systems have worked by using light for the wavefront sensing that's at a different wavelength than the light that you're using for science. So if you take that approach, you're not necessarily sacrificing any of your science light, you're just using light that would otherwise have been unused. That has some cons. So for example, there will be parts of the wavefront aberrations that are just chromatic, and so you will not be effectively correcting those with your wavefront sensor, and that might ultimately limit your contrast or be a factor that limits your contrast ratio in the final science plane. Then the other part of your question had to do with sort of the speed element. So this has long been a huge challenge for ground-based high contrast imaging systems. The fact that they are oftentimes limited to very bright guy stars, because you need to have sufficient signal to noise on your wavefront sensor to be running your AO loop at 1 kilohertz or even 2 or 3 kilohertz with state-of-the-art systems. And there just aren't that many stars that are bright enough. So systems like GPI and Sphere were limited respectively to something like I magnitudes of 9 and 10 for GPI, and then R magnitudes of, I want to say 13, 14 for Sphere. Someone can correct me if I have those slightly wrong. But this is a huge challenge. And so I think understanding how to make the most effective use of the photons that we have is something that's very important. And so wavefront sensors like the Zernike that are very photon efficient are one way to start addressing that. We are getting better and better detectors to use for our wavefront sensing. So for example, that have lower read noise and that can read out more quickly. The other component is we can choose, we can optimize the wavelength that we're doing our wavefront sensing at based on our specific science star. So for example, if you're on a ground-based telescope and you want to do high contrast imaging around very red M dwarfs, for example, at L or M band, you might want to do your wavefront sensing not in the visible, but maybe in the H band. So this is something that LBT and Keck, and I think now Subaru are all doing to address that.
Thanks.
Great. You can just go over there so that.
Hi, I just had a quick question about when you were talking about laser guide stars. Obviously, turbulence directly toward the target of whatever you're observing is going to be a little bit different from turbulence slightly to the sides, a little bit away from wherever that is, wherever you're pointing your guide star, right? So how do you find the trade-off between how far away your guide star is from your point of observation so that your guide star isn't too close to contaminate your data, but it's also not too far to get bad information about your the wavelengths that are coming in, the turbulence that's coming in?
Yeah. So, okay, there are a couple of different parts to that question. So the first part has to do with, can your laser guide star be too close to your science star? Unfortunately, the answer to that is no. You can point your laser right at your science target, and because you're typically observing, you're doing your science and wavefront sensing at different wavelengths, and because the focus of that laser light is going to be different than the focus of the starlight, you can get away with having them be co-located. So then the question becomes, how far away can you have your science object? Something that I didn't mention here is that when you're using a laser guide star, that doesn't completely eliminate the need for a natural guide star. Laser guide stars cannot measure atmospheric tip tilt or the bulk motion of the PSF. So you still need a real star to use for your tip tilt. And so because you can point your laser right at your science object, the question becomes, at what angular separation can you get away with identifying a tip tilt star? And this has to do with the isoplanatic angle. And this is the critical angle over which you can still sufficiently measure your tip tilt or any kind of wavefront aberrations. And that is, again, a quantity that you can use these parameters from turbulence theory to quantify. So a good resource for deriving the isoplanatic angle is the Adaptive Optic textbook by Hardy. Or also if you go to cfao.science.ucsc.edu, we have a resources page to learn more about that.
Right. Do you have a super quick question?
Okay.
Yeah.
Hi, my question is about the wavelength dependency. So if we use integral field spectrograph, how can we deal with the wavelength dependency because we take image in different wavelengths simultaneously?
Yeah, that's right. So oftentimes when we're talking about chromaticity as an error term in our AO error budget, we're talking about the difference between the wavefront sensor's wavelengths, maybe that's in the R band, and the science wavelength, and maybe that's in the JHK band. And so that the distance between those two wavelengths is usually much greater than the wavelength coverage of your IFS. So usually that's not a component that dominates this.
Okay, thank you.